So welcome back, and let's talk about methods and what are actually the pitfalls and problems of counterfactual explanations. So we will see two strategies in that video to generate counterfactuals, and then we discuss these kind of problems and mutations. So let's start with an overview again of how actually different kind of methods for generating counterfactuals differ actually. And you will see actually, if you're looking it up, Google Scholar, for example, or other sources, that there are many kind of techniques for generating counterfactual. That's not too surprising, right? The way we introduce that, we have different kind of targets and objectives, and we have more or less, and everything depends a bit on your input and your application and so on. So let's see that a bit more concretely. So first of all, of course, the method can depend on the target. So most of them right now focus on classification models and less of them actually on regression models. And more or less all of them are in the supervised learning paradigm, which makes somehow sense because if you are not able to say, yeah, let's change our predicted value to something which is more desirable, what should be then actionable, or what should be the objective in changing stuff, right? So it's a bit more complex the moment you're going away from supervised learning, but there are also ways doing that. Then data. The methods mainly focus these days on tabular data, which is still in industry one of the most prominent way of representing data. There are some for visual and text data, but so far as we know, there's no CE method for audio data. The feature space, most of them have numerical features. Few of them can process mixed features, so numerical and discrete ones. So you also have to watch out actually what kind of data set and feature space you are working with. Next, let's talk about the objectives. So we have seen already these different kind of objectives, which are then, for example, in the prediction space or the feature space, but also we talked about plausibility and sparsity. And really depending on the methods, some take more of them into account, some less, some have some additional ones like fairness or individual preferences, right? So really check what kind of objectives are in the methods you're using. Next is model access. So some of these methods really working on the complete model internals, so really knowing the entire structure, all the weights and everything, that you can really compute gradients. And some are more on this black box view that you can only query and getting some of the predictions of your underlying model. But it really depends again a bit of what kind of assumption we're making. Then also how we optimize actually and getting our counterfactual, given that we defined all our objectives and now what kind of model access we have. We can of course only use gradient-based methods if we have some kind of access to the differential model, or we try to approximate that. If we have linear models, we could use something of mixed integer programming. If we have more in this black box view, often people going there for gradient-free algorithms, LMU or genetic algorithms actually. And we also discussed already the threshold effect. So many methods return actually a single counterfactual example per run. Some return multiple of them. Other prioritize CEs or let the users actually choose. So it depends again a bit, right? Keep that in mind the moment you are choosing something. What would you like to achieve with these CEs and what is interesting maybe for you or your customers. So let's talk about two different kind of methods for generating CE. A more traditional one, I would say, is from 2018. And here was the counterfactual introduced in the context of machine learning predictions by solving the following equation. So we had that already more or less before, right? So we have this objective in our prediction space, simply saying, yeah, would like to achieve that. We're now going to the desired outcome, right? So y prime was defined by the user, that is what we would like to achieve as an outcome. And actually now we have to find x prime, given f hat our model, that we can really achieve y prime, right? So the difference should be small. And here's an A2 loss. In addition, we had the objective in the feature space, and here what it's simply doing is simply, we know that we have xj given, right? And that's what we are starting with. That's the point we'd like to start with for generating a new counterfactual. And now xj prime, that's what you would like to optimize, should be more or less close to that, right? The difference should be small. That we now can scale that for different kind of features. So we have here the sum over all the features. We're scaling that by the median absolute deviation of feature j. How is that solved? Yeah, so that's more the black box view. NADE was simply used for solving that equation. Now the question remains actually, what do we do with here our weighting constant in that equation? And the idea is then simply that we increasing that until we have a sufficiently closed solution. So, right, so we would like to definitely ensure that part with that algorithm. So we would like to maximize lambda, that's really ensured. So we see that as a top priority, and the objective in the feature space more as a secondary objective. Has nevertheless some shortcomings, that approach, right? So we do not really know how to choose that lambda a priori. How should we? Because we don't know how everything is scaled actually and so on, how important or easy it is to get to our desired outcome. So that's the reason why I maximize the lambda, but as it really leads to that we only trying to optimize that first part, right? As it's really the primary one, that could lead to circumstances where then x prime is very far away from the original x, right? Furthermore, the way we're scaling here in our feature space is only covering numerical features, so that simply means that the objective for the feature space is really only applicable to numerical features. We discussed already other objectives like sparsity, plausibility, which are here simply neglected. Let's talk about the second approach, which really goes from a completely different kind of direction and saying, yeah, we have different kind of objectives, so why not simply defining that as a multi-objective problem? So we would not like to collapse everything into a single objective, so right, that's more here, it is a single objective. We're scaling simply or weighting our objectives and putting it to one number in the end. Here saying we have 4 different kind of objectives. Let's try to optimize them and find a Pareto front, right? Pareto front was simply, let's do that for two-dimensional or two-objective case. We have 2 objectives and would like to minimize them. We have different kind of points, right? Each of these points gives us a different kind of x prime. And what we would like to know is what are the most dominant ones of these points dominating all others, and that's then something like that, right? Roughly saying we really don't care about these because all of these here on the Pareto front are actually much better because they dominate everything else, right? What they're doing simply now is using a multi-objective genetic algorithm, NSGA2, to produce these kind of sets. And important is more or less, if you're trying to come up with these, that you have full coverage more of the Pareto front, right? It's not useful if all of your points in Pareto fronts lies here and you completely ignore that upper part, right? You would like to be fairly diverse. In addition, you would like to be diverse also in the feature space, of course, that you don't have only similar kind of counterfactuals. Good. So here an example where they applied that idea. So the model, as again, was trained on the credit data. We have here an SVM again with an RBF kernel. We have a data point which was giving us actually a credit score of 0.34 of being a good customer, and of course the customer would like to increase that credit score, let's say would be at least above 0.5. They were now running that multi-objective CE algorithm. They found after 200 iterations of their NSVA2 algorithms, 69 different kind of counterfactuals, which is quite nice, right? So let's look into them a bit. What they're doing, we're now saying that they are visualized first in a parallel coordinate plot and a two-dimensional surface plot. And what we can here, for example, see that another plot, here's the parallel coordinate plot. Oops, sorry, that was the wrong one. That they only changed more or less two of the input features, that's duration and credit amount. You can see a bit like how it scales. So for example, duration amount is between 9 months and 48 months. Credit amount is between roughly 6,000 and 1,649. And then we can see, okay, changing here between these two really helped, and going more or less to a bit lower duration seems also to help. I forgot to mention the one here at the top line, that was the original X. We can also try to plot this in these surface plots, as I already mentioned. So again, duration and amount of the credit. We starting over here actually, that's the point of X. And here we see all the counterfactuals, which makes sense, right? So we would like to go here in a region which is color-wise more to the more bluish color, not so dark. And which is also nice that we focus here a bit on that region actually where we also have a lot of training data. That comes simply by optimizing also the possibility constraints, right? We were saying, yeah, of course, we should try to go closer to our training data. That's really plausible what we're trying to achieve here, that someone can actually do that in practice. It's more actionable. Good. So let's start to discuss problems and pitfalls and limitations. Actually, there are quite some of them. I will quickly go over these and give you some intuition on these. So first of all, counterfactual might give you an illusion that you really understood the model, right? But what we're actually only doing is going from one point to a different point, x prime. But what really happens in between here, you don't really know. And as we said, we can also sometimes go to a different kind of x prime and so on. It's not really giving you an understanding what the model is doing. It's only giving you an alternative point, more or less, in the space. And that might be really improper and really understanding what the model is doing, right? So you would need to start actually from many of these points x, and then checking many of the counterfactuals if you would like to have a chance to understand that. Also, we talked about similarity measures already. For example, we could use these A1 metrics, which is somehow reasonable for tabular data, right? That makes sense, but for image data, we'd like to use something else maybe. Also saying, yeah, let's go for sparsity can be maybe nice for your end users. So because then if it has to be actionable, right, you don't have to take too many of these features into account. But on the view of someone developing your model, so the data scientist working with that, if it's too sparse, maybe we're missing model bias actually. We talked already about that we can't confuse counterfactual with really understanding the real world. It's only giving you some insights on the model we'd like to explain, right? Also, what could happen is actually that we discuss too much information, right? So if an attacker can query your counterfactuals over and over again for different kind of points, it can maybe read too much information and therefore then try to come up with something which was not intended. We also talked about the Rashomon effect already, right? So how many of the explanations, counterfactuals we should return to the end users. Then there is actually no perfect solution, right? So if you have too many of them, people will become confused and don't know what is now expected from them. If there's too little, maybe they might fear that they don't really have a choice anymore and also don't accept that. So there's a weird trade-off which is hard to deal with. Also, if you're thinking about actionability again versus fairness, we have here a bit the problem that I was always arguing for that counterfactuals should be actionable so that you can really act on it. But if you're thinking about that, maybe your data has something on the ethics of where you're coming from or so, saying that maybe we have some kind of information that someone is from Africa or Europe or North America or Asia and whatnot, right? And we're saying that, of course, we can't change that, right? I'm from Europe and I will never change that in my life. So it's not actionable to really go in that direction with counterfactual. However, if we forbid that, we can't really figure out that there's maybe a racial bias in our model, right? And so we will never see anything in that direction. So that could be also a problem. Furthermore, we talked about that part also already briefly, is saying, of course, if you're now saying your actual recourse is to wait for 1 year and then you're getting your loan, maybe the underlying model will have changed by then, right? So you can't assume that everything you're getting from a counterfactual will also hold true the next year, the next decade, or maybe not even the next day, right? Also coming back to attacking counterfactuals, there was also be shown that researchers can create models with great performance actually, which generate arbitrary explanations using CEs specified by the machine learning developers. So saying you could, for example, try to hide bias again and so on and so on, which makes it very hard to really trust them if you don't trust the machine learning developer in the first place.